Some of you may not quite be done, but let's take a look and see what we got for these anyway. So for the mean, we have to add them all up and divide by how many are there. So first of all, what does n equal here? 5, because there are 5 numbers in our list. So to find the mean, we're going to add them up. 17 plus 9 is 26, plus 24 is 50, plus 11 is 61, plus 14 is 75. Divided by 5 gives us 15. So we've got a mean of 15. Any questions so far? Yes. There might be a few more numbers, but yeah. The median. What do we have to do for the median? Put them in the order. So it's going to be 9, 11, 14, 17, and 24. Then what? Some of you just crossed off the ends until you got to the middle. And that works. Obviously, you can just look at this one and see that 14 is in the middle. Or you do n times 0.5 or n times 1/2. 5 times 0.5 is 2.5. Since that comes out to be a decimal, you round it up to the third number. So the third number is 14. So 14 is the median. This tells us, by the way, that our data set is skewed to the right, because the mean is larger than the median. Okay, next, the range. The range is simply the largest minus the smallest. So 24 is the largest, 9 is the smallest. The difference is 15. Any questions so far? Oh yeah, the standard deviation is where the fun really begins. We've already completed step 1. We have found the mean, which is 15. So now we're going to write the numbers down here. It doesn't matter whether you write them down in order or not, as long as you have all of them. What is step 2 going to be then? Subtract the mean from each. 9 minus 15, negative 6. 11 minus 15, negative 4. 14 minus 15, negative 1. 17 minus 15 is 2. And 24 minus 15 is 9. Now, we could double check this. If we added those up, it should come out to 0. Again, that's not really part of the calculation, but it's a way to double check ourselves here. Those do add up to 0 right now, by the way. What's step 3? Square them. What's negative 6 squared? 36. Negative 4 squared? 16. Negative 1 squared? 1. 2 squared? 4. And 9 squared? 81. What is step 4? Add them all up. We get 138, is it? Okay. So then 138. What is step 5? Divide by 4. Times divide by n minus 1. Since n is 5, it is 4. Which is going to give us 34.5. Now that would be called the variance. To get to our standard deviation, we have to go one more step. Square root of 30. What is it? 5.87. Perfect. Yep. 5.87 should be good enough for that. We'll round. Remember I said for standard deviation and measures of Spread, we go 2 digits past the data. So since the data was given to the nearest one, we would round to the nearest hundredth. And for measures of center, you go 1 digit past the data. So we'd go to the nearest tenth for mean and median. Now I didn't do the mode here because there was no mode. None of the numbers were repeated. But mode is just the one that appears the most often. Just for fun, why do people like scoff when I say that? Let's say we surveyed a group of people to see how many cars they own. And let's say we had 7 people that said 0. We had 34 people that said 1. We had 7 people that said 2 cars and 2 people that own 3 cars. Find the mean, median, and standard deviation. I'll give you a few minutes to work on that. Let's see how we're doing. Did we get an answer for the mean yet? 1.08. How about for the median? Don't know yet. I have to check it to see what. How about for the median? Most likely 1. Let's go through the mean and median first, because if you don't have the mean right, your standard deviation calculation is not going to work out, right? So one thing we're going to find is we're going to find the total frequency here, which is what? 50. Good. Next thing we're going to find is our number times the frequency. So 0 times 7 is 0. That's saying we have 7 zeros that would add up to a total of 0. We have 34 ones, so 1 times 34 is 34. We have 7 twos, so 2 times 7 is 14. And we have 2 threes, so 2 times 3 is 6. That adds up to 54. So the mean is the 54 divided by the 50, which is 1.08. The median, if n is 50, we have to do n of 50 times 0.5, which is 25. Since that comes out to be a whole number, that's telling us it is between the 25th and 26th number. Well, just going up here, we can easily find the 25th and 26th. The first 7 numbers are zeros. If we're listing it out, that'd be 7 zeros, right? The next 34 numbers are ones. Well, 7 plus 34, that takes us up to the 41st number, right? So that's telling us pretty clearly that the 25th and 26th numbers are definitely both ones. In fact, the 8th through the 41st numbers are ones. So the median is definitely a 1. Do you guys want another minute or two to work on the standard deviation? Okay, we'll give you another couple minutes on the standard deviation. Okay, let's try this. So our next step is we're going to take the number minus the mean for each. So 0 minus 1.08 is a negative 1.08. 1 minus 1.08 is negative 0.08. 2 minus 1.08 is 0.92. And 3 minus it is 1.92. So any questions on where those numbers came from there? Next, we're going to square those numbers. Negative 1.08 squared is 1.1664. 0.08 squared is 0.0064. 0.92 squared, 0.8464. Thank you. 1.92 squared is 3.5864. 6864. Okay. Now then, this is where we have to add the step because of the frequency table. We have to do the square times the frequency. So 1.1664 times 7 gives us 1648. 34 times 0.0064. 2176. 7 times 0.8464. 9248. And 2 times 3.68. 3728. Now we can add those up. If we add them up, we get 21.68 exactly. Cool. What do we do with that then? So we're going to divide by n minus 1. N is 50. So we got to divide by 49. That's where it went off the tracks for you. So 0.4424. And then the final step, square root of that. 0.6652. You may have did 0.67 or 0.665. Any of those three I would accept. Okay. You guys are actually writing it down. I've got some classes they'll pull out their cell phones at this point and take a picture of the board. There are. Can you zoom in well enough so it's not blurry? Okay. Okay, so that's our review from last week. Now I want to talk a little bit about how does this all fit together? What does it all mean? Well, there's a lot of larger implications of this stuff when we get into inferential statistics. So we mentioned last week, inferential statistics is where we take this stuff and go on to use it to make decisions. Well, we're not going to get into that part. We're going to stick with the descriptive side of it. But one thing that we can use it for, that it does help us, is something called the empirical rule. The empirical rule goes back to this bell curve. And if our data is normally distributed, in other words, if it follows a bell curve type distribution like this, it has very definite patterns with the mean and the standard deviation. In fact, very definite patterns with any measure of center and then the standard deviation going off of that. So the center of this curve is the mean or the median. We tend to use the mean just because it's usually the first thing calculated. Then off of that, we take steps out one standard deviation at a time. So we'd have the mean value, we'd go down by one standard deviation. I'm just going to go -1 SD, down by a second standard deviation, and a third standard deviation. And I'll fill in some details here that makes this more clear in a second. Going the other way, we'd take steps that go up by 1 standard deviation. So plus 1 standard deviation, plus 2 standard deviations, and plus 3 standard deviations. And if you go up in those steps, the percent of the data that falls in each range is constant, no matter what the mean and standard deviation are. So for a normally distributed set of data, there will always be, now this book, by the way, uses something called the exact empirical rule or the detailed empirical rule. I usually teach something called the approximate, just because it's easier to remember. But we'll go by with what this book says. Between the mean and 1 standard deviation away from the mean is approximately 34% of the data. The detailed version is 34.13% of the data. And that's true on both sides of the mean. So 34.13% of the data falls between the mean and 1 standard deviation below it. Another 34.13% falls between the mean and 1 standard deviation above it. So that would mean between 1 standard deviation on each side of the mean, that would be 68.26% of the data. Between 1 and 2 standard deviations on each side is 13.59%. And then between 2 and 3 standard deviations on each side is 2.15%. And finally, outside of 3 standard deviations is only 0.13%. Well, let's make this a little bit clearer, hopefully. This is general. This is always true. What would change would be the numbers we end up putting in here in place of those general labels. For example, let's say that you are looking at buying a house. You want to buy a 3-bedroom, 2-bathroom home. And you do some research and you find that in the area you are looking to buy, of all of the 3-bedroom, 2-bathroom homes that have sold in the last period of time, the mean is $120,000. And the standard deviation, let's go with $25,000. So what that's going to mean for us here is on this curve, the center, the mean is 120,000. If we go 1 step down, that's 1 standard deviation down, we subtract 1 standard deviation from our mean. The mean's 120, standard deviation is 25. So we subtract, that gives us 95,000. Well, our next step down, we subtract another standard deviation, a second standard deviation. So 95 minus 25 gives us 70,000. And we go again, we subtract that standard deviation again. 75 minus 25 is 45,000. Going the other way, above the mean, we add a standard deviation. So 120 plus 25 is $145,000. Another step, we add a second standard deviation. So 145 plus another 25 is 170,000. And then again, adding another 25, 170 plus 25 is 195,000. So what does this mean? Well, let's say you find a house that you just absolutely fell in love with. It's 3 bedrooms, 2 baths, and the price is $170,000. Your realtor tells you this house is going to sell fast. You better put an offer in right now. Don't try to negotiate price because there's going to be all sorts of people putting in offers. You better jump for it before somebody else puts in a better offer. Well, what this curve tells you, $170,000 is right here. That's this divider right here. If we add up all of the percents down here, that is going to add up to 97.72%, I believe. So that is telling you is 97.72% of all 3-bedroom, 2-bathroom houses that have sold in that area in the last period of time sold for less than $170,000. Which means one of two things. Either this seller is probably going to be willing to take less than $170,000, or you'll probably be able to find a different house that you still like that's cheaper than $170,000. The other way you could look at it is the other side. If I add these percents together, that's 2.28%. That's telling you that only 2.28% of all houses that have sold in that area were more expensive than that. Well, let's look at some other numbers that we can get out of this. Let's say we ask what percent of houses would you expect to sell for, let's say, between $95,000 and $145,000. Well, up here from $95,000 to $145,000. 95, 145. Goes from there to there. If I add up those percents, I get 68.26%. So I expect over 2/3, 68.26% of those houses that are 3-bedroom, 2-bath to sell between $95,000 and $145,000. How about less than $95,000? Let's say you decide your budget is really $95,000. What percent of the houses will be less than that? Here's $95,000. If I add those up, they'll add up to $15.87%. So if my budget is only $95,000, only a little under 16% of the homes will be in that price range. Any questions? Okay, so let's do a similar thing here. Let's say that you receive a test score. Your test score is a 93. And you want to know, is that a good score or a bad score? Well, this curve does not change. I didn't say 93 out of what, by the way. Doesn't really matter. We still have the center of the curve. This is still 34.13% on each side for the first standard deviation. This is still 13.59% to the second standard deviation. And this is still 2.15% from the second to third, and only 0.13% outside. Now, we need some more information to make this any more detailed. let's say that you find that the mean of all students, or of all people who have taken this test, the mean is 79. And the standard deviation is 14. So what I've put up here so far, the bell curve and all these percents, this part is a constant. It never changes. What changes is what I'm about to put on here from this information, from the mean and standard deviation. What number is going to go in the center of this curve? 79. If I go over here, what has to go here? 65. 79, the mean minus a standard deviation of 14. What goes in this next spot? 51 minus another standard deviation of 14. And this next spot? 37 minus another standard deviation of 14. If we go up this way, what has to go here? 93, that's the 79 plus a standard deviation of 14. How about here? 107, and here? 121. Now your score was 93 right here. That's where you ended up. Which means if we add up these percents here, you scored better than 84.13% of the people that took the test. Or you could look at it the other way. If you add these up, only 15.87% of people who took the test did better than you. Does that make sense? So this empirical rule is actually a pretty powerful tool that allows us to look within data and figure out exactly how it should be distributed. So that center and spread calculations we talked about last week allow us to get a little better picture of the data when we put them into this empirical rule. The mean wage in the area is $13.90 per hour, with a standard deviation of $1.80 per hour. What percent of workers would you expect to earn less than $10.30 per hour, 2, more than $15.70 per hour, or 3, between $12. Now let's make this a little bit more meaningful. Let's do $10.30 per hour and $15.70 per hour. I'm going to give you guys a couple of minutes to work on that, and we'll talk about it in just a minute or two. Okay, so let's look at our bell curve and get the numbers put in here. What goes in the center here? 1390. What goes here? 1210, and here 1030, and here 850, right? How about here? 5070, and here 1750, and finally here 1930. So I know that's a little bit small to read, but come on now. So for the first one, less than 1030, that's right here. We add up those percents, we get 2.28%. Good. The next one, more than 1570. You got it. We add those up as 15.87%. And then between the 1030 and the 1570 is right in here, yes. 81.85%. If we were to add those 3% up, what do we get? Somebody got it back there? It should be 100% because it covers the whole curve, right? Perfect. And I think they do add up, don't they? Yeah. So that's our bell curve with the empirical rule. It is time for a break, so let's go ahead and do that. We'll come back in 10 minutes at 6:30. Continue this time. So we've been doing this empirical rule with the mean and standard deviation. But the weakness we have with it is if our values fall between these set numbers on the curve, between those standard deviation steps, it really doesn't tell us a whole lot. Let's say that you are getting $14.20 per hour. Well, that falls well between two values here. And we can get some information. We know it's slightly more than 50% that's less, but we don't know how much more. We don't know how it splits up that section that it's in. So there's another tool called the Z-score. If you've ever read something and it says normalized data, it's using Z-scores. It is basically comparing it back to itself. And what Z-scores actually are they're ways to compare two things from different populations. So I should actually say two or more items from different populations. Let's do the simple example here of test scores again. To get into school, well, you had to take a few tests, but let's say you had to take two tests. You had to take an English test and the most important one, the math test. Let's say your score on the English test was a 72 and your score on the math test was a 59. Does that mean you're horrible at math, should go home crying and forget about it? Everyone's like, yeah, can I go now? No, because there's no comparison between these two numbers. Because we don't know. Maybe the math test was just a lot harder than the English test. So we use something called a Z-score. A Z-score compares that number back to its own population. It is equal to the number, we're going to call it X, minus the mean of its population, divided by the standard deviation of its own population. So let's say that for the English test, the mean score of all people who took that test was 60, with a standard deviation of 8. Let's say for the math test, the mean score of all people who took that math test was 44, with a standard deviation of 7. When we look at this, your English test, you were 12 points above the mean. Your math test, you were 15 points above the mean. Does that mean you're better at math? Not necessarily, right? Yeah, what we have to do is we're going to do that Z-score. The standard deviation allows us to measure how far above the mean we are. And that Z-score is the tool that gets us there. So the Z-score for our English test, what was the value for the English test? 72 minus, what's the mean? 60. And it'll be over the standard deviation, which is 8. So 72 minus 60 is 12. 12 divided by 8 is 1.5. You get a Z-score of 1.5. What that is saying is your test score of 72 is 1.5 or 1.5 standard deviations above the mean. So that's pretty impressive. Bless you. So we're 1.5 standard deviations above the mean. That's pretty good. And if we look back at this curve, 1.5 standard deviations is somewhere in here. We're way more than 85%, better than 85% of the people there. Well, let's now compare it to the math score. The Z-score in the math test, what was their value? 59. What is the mean? 44 over the standard deviation of 7. So we go ahead and we'll subtract 59 minus 44. 15. 15 divided by 7 is 2.142857. We'll just go 2.14. How does that sound? You were 2.14 standard deviations better than the mean on the math test. Which one's more impressive? The math test. Okay, so that's a little bit more useful, practical application of this. Analyzing your test scores isn't necessarily a great application. That's something you're going to do every day. But let's say you want to compare 2 job offers. Job A and job B. That is the height of my creativity at this point in the day. Job A is offering you $11.90 per hour. Job B is offering you $16.20 per hour. The difference is they are in different cities, different states. We're going to ignore moving costs, but we are going to use a standard of living measurement, a cost of living measurement. And what we're going to use for cost of living measurement is the mean salary or the mean wage in each place. So in the location of job A, the mean wage is $10.90 with a standard deviation of $1.20. In the location of job B, the mean wage is $14.70 with a standard deviation of $1.80. Which is a better job offer? Well, let's test it out. Let's look at the Z-score for job A. We do 1190 minus 1090 divided by 120. Well, 1190 minus 1090 is $1. Divided by $1.20 is 0.83, right? So you are 0.83 standard deviations above the mean, which are still better than average. Let's look at job B. Where do we start? 16.2 minus 1470 over 180. So we subtract 1620 minus 1470 is $1.50 over $1.80. They're exactly equivalent job offers. I couldn't do that again if I tried. Now, there are obviously other considerations here. Let's say this one came out to be 0.8 and this one 0.85. Well, that close, then the salary, the wage itself probably isn't a huge factor. You might want to look in quality of schools, crime rates, stuff like that. There might be other factors. So, I mean, in this case, they're a dead heat. They're both the exact same Z-score. So those other factors would have to make your decision for you. If they're negative, well, that's going to be our next example. Good question. Let's say you have a job as a store manager. You are going to fire one of your salespeople. Let's make it Bob and Steve. Somebody always sings that little jingle when I say those names. Those are my go-to names whenever there's a pair of people that are making mistakes. You decide that what you're going to do is whoever has the worst performance in the next week is out the door. So Bob's sales is $2,400 this week. Steve's sales are $4,100. Does that mean Bob goes bye-bye? No, we have to look at the comparison. Let's say Bob works in toys, and the mean sales for all people in toys was $4,200. With a standard deviation of 700. Steve works in electronics. Let's say the mean of all salespeople in electronics was $5,900 with a standard deviation of $600. I want you guys to take a minute here and decide who you would fire, and we're going to talk about this in a minute. So for Bob, the Z-score, well, 2,400 minus the mean of 4,200 divided by a standard deviation of 700. So we subtract there, that is negative 1,800 divided by 700, 2.5714286, right? Negative. So what that's telling us is Bob, since it's negative, is 2.57 standard deviations below the mean. Not very good. Let's look at Steve. So we're going to take 4,100 minus 5,900 over 600. Steve, we subtract as a negative 1,800. 1,800 below the mean. Divided by the 600 is a negative 3. Steve is 3 full standard deviations below the mean. Bye, Steve. Yeah, chances are if Bob is performing that poorly, I am probably, well, I might be firing only Steve right now, but I'm still looking for somebody to replace Bob too. Kind of an economic principle, if you take any stuff on management and personnel management, a good business should always be hiring, because you're always looking to hire somebody better than your worst employee. You know, it's that constant improvement. You don't have to hire somebody better than your best to improve your workforce. You just have to hire somebody better than your worst. Okay, so that's our measures. The Z-scores actually is an example of one measure of position. And you're measuring the position within its own population so that you can compare them. Another measure of position that can be used to compare numbers is something called a percentile. You've heard percentiles all over the place, most likely. If you took a test, you heard you tested in the 82nd percentile. Or if you have had kids, you've taken them to the doctor and said their weight is in the 61st percentile for their age group, or their height is in the 42nd percentile for their age group, or whatever. What's that? Well, 42nd doesn't necessarily mean that they're tiny, but if they're down in the 20s, it would mean they're on the small side. Always on the bigger side. So what a percentile means is the percent of items in the population with a smaller value. So let's say you have your child in and you're told that they are in the 91st percentile for weight. What that means is 91% of all other children their age weigh less than them. What that's saying. You know, they might be in the 95th percentile for height too, you know. So let's look at these percentiles a little bit. First of all, let's look at finding the percentile, or finding the number that is in a certain percentile. Now, the first step in dealing with percentiles, just like with finding the median, is to put the numbers in order from smallest to largest. So the data set that I'm going to give you is just going to be in order from smallest to largest. I'm going to put it along the bottom of the screen here so I've got room to work both above and below it. So there's my list of numbers. Now you look at that, that looks like a large set of numbers, and it kind of is, but when we're dealing with percentiles, we're usually dealing with data sets of thousands of numbers. And the calculations make a whole lot more sense when you have a lot of numbers there. So if I had a set of only 5 or 6 numbers, the percentiles would not make much sense at all. Now, just to make this a little bit quicker for me, I'm going to number these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. By the way, n equals 14. Find the /80th percentile. To find the 80th percentile, first step again is to put them in order from smallest to largest. We've already done that. Second step is to find the position. This is why we did it the way we did with our median, because the position is n times the percentile. So here that's going to be 14 times 80% is 0.8 is a decimal. So that is what, 11.2? For the median, if that came out to be a decimal number, what did we do with it? We rounded up. So the 12th number in the list is the 80th percentile. The 12th number in the list is 50. So the 80th percentile of that data set is 50. What that is saying is 80% of the data is smaller than 50. Let's find the 35th percentile. So what are we going to do for that? Yeah, 14 times 0.35, which is going to give us, what, 4.9? So 4.9, which is going to round to the 5th number in the list, which is 27. So the 35th percentile is 27. 35% of the data would be expected to be smaller than 27. In your notes, I'm going to have you find the 75th percentile and the 50th percentile. We'll talk about those in just a second. I'll give you a minute to find them. So the 30, how many numbers are smaller than 30? 5. How many are equal to 30? 1. So that's 5.5 over 14, which is 0.39. That's the 39th percentile. Any questions? Other than make it stop? Okay. So that percentile is a relatively powerful tool. Now, from those percentiles, there are several related calculations. Do you guys have a question over there? No? Are you sure? Okay. We could call it 39 or 40. You know, either way it would be fine. Yeah. Well, when you're dealing with position is always rounded up. Even if it's like 7.2, it still rounds up to 8. But percents, it's not. It's a little bit less clear. Yes. Yep. Yep. Okay, so the formula is the percentile is equal to the number that are smaller plus 1/2 times the number that are greater divided by n, which is the total number in the list. So here there are 5 numbers that are smaller than 30. There's only one that is equal to 30. And then 14 is how many numbers are in the whole list. So like when we did 27, there were only 3 numbers that are smaller than 27, but there were 2 27s and 14 total. So it's 3 plus 1/2 times 2 is just 1. So 3 plus 1 gives us 4. And 4 divided by 14 gives us the 0.2857. So we rounded that to the 29th percentile. Does that make sense? The 14 is, there's 14 numbers in the whole list. Yep. There is no greater than number in this one, no. It's just smaller than and equal to. Yep. Any other questions? Okay, so now related to these percentiles, we have something called quartiles. Quartiles divide the data into 4 equal pieces. Now, let's say you're going to take a piece of string or a board or whatever, and you're going to cut it into 4 pieces. How many cuts do you have to make? 3 cuts. If this is my board, to cut it into 3 pieces, 1, 2, 3 cuts. So there are only 3 quartiles. Only takes 3 cuts to cut the data into 4 pieces. Quartile 1, or the first quartile, is just the 25th percentile. Quartile 2, or the second quartile, is almost never called the second quartile because it is the 50th percentile, which we saw earlier is just the median. So we almost never say find the second quartile, we say find the median. Quartile 3, or the third quartile. Anybody want to guess? 75th percentile. So it cuts the data into 4 equal pieces, each of them 25% of the data. So for our set of data that we had up here, we'll make a new set of data. I'm going to put these in order from smallest to largest again because that's the first step in finding your percentiles and your quartiles. So let's do 7, 11, 12, 14, 14, 15, 18, 19, 20, 24, 30, 35. Let's see what I have there. I'm just going to number them here just to make it easier. That'll work. We got 12 sets. So n here equals 12. We have 12 numbers in our data set. So quartile 1, affectionately abbreviated Q1. .25 times n of 12 is 3. Since that's an integer, it is going to be between 3rd and 4. So that's going to be 12 and 14. Add those together and divide by 2, you're going to get 13. Bless you. Our second quartile, or our median, is going to be 0.5 times 12, or 12 times 0.5 is 6. So since that's an integer, it is between the 6th and 7th. 6th and 7th is 15 and 18. Yeah, 15 plus 18 is 33, divided by 2 is 16.5. Is the median. Our third quartile, 12 times 0.75, or 0.75 times 12, gives 9. So that means it is between the 9th and the 10th. So yes, 20 and 24. So we'll go ahead and add those. 20 plus 24 divided by 2 is 22. So what does this mean? Well, this is actually part of something called the 5-number summary. The 5-number summary is those 3 numbers plus the minimum. What would be the minimum in this data set? 7. And the maximum. What would be the maximum in this data set? 35. So what we would do is make a plot. It's called a box plot. Sometimes called a box and whisker plot. And what it looks like is basically it's a number line. Pretend that's a line. So here's our number line. And we plot the minimum. Well, we plot the 5-number summary here. So the minimum is 7. I'll make a dot there. The first quartile was 13. I'll mark that. Then it was 16.5 was the median. 22 was the third quartile. And the maximum is 35. So what we do to make this plot, we actually make a box that goes from the first quartile to the third quartile with a line at the median like that. Hence the box name in the name of the plot. Then the whiskers go up to the minimum and to the maximum. What this shows us is how spread out the data is. You can see the plot is actually in 4 separate sections. The smaller the section of the plot, the tighter the data is, the closer together the data is in that spot. So where is the data the most tightly packed here? Right there, that's the smallest section of the 4 sections. So between the first quartile and the median, the numbers are closest together. Where they're most spread out is between the third quartile and the maximum. If you look at analyzing, oops, is there a question? If you look at analyzing data sets in business and comparing them, these box plots are a big comparison. For example, let's say I have a second plot here of a second set of data. They look something like this. What this tells me, first of all, the pieces of the plot are smaller. So it tells me the data is more tightly packed together in this plot. This wing's a little bit longer than it was in the original, and so the data is a little more spread out on the bottom. This one's a little shorter than it was up above, so it's not quite as spread out on the top. What if I have a plot like this where all 4 sections are exactly the same size? What does that mean? The data is pretty much evenly distributed throughout it. What shape would we expect the bell curve to have? First of all, we'd expect it to be symmetrical, and we expect the data to be more tightly packed in the middle because the curve is higher in the middle. That means more numbers are in the middle. So we'd expect it to be something like that. I don't have any more time to talk about box plots, but there's a lot of stuff we could talk about with them. It's a powerful tool, but that's your introduction to them. We're a minute and a half or so early, but let's go ahead and take our second break there. When we come back, I want to spend a little bit of time talking about probability, basic probability, and then I will have some time tonight to go over and answer anybody who has not managed to finish their corrections. I'll answer any questions on the test that you need me to go through. Okay, folks. So for our last little section here, to wrap up probability, just to give you guys a little view ahead, by the way, test corrections, I'd like to have those in 2 weeks from tonight at the latest. Your next test is 3 weeks from tonight. So we do have 2 more weeks of lecture on this section before we have our test. Something like that. So let's see here. 25th, I believe, is when the next test should be. Well, let's on October 24th and 25th are in-services, college-wide in-services, so there are no classes that day. So we will have 2 more lectures, and then you guys will have 2 whole weeks to study for that test on the 1st. So I'm expecting wonderful grades for that. Oh, 2 full weeks. No, there won't, if there's no class, there won't be a quiz. But yes, I'm glad somebody brought that up. There is that week. Tuesday and Wednesday. I know that's kind of a weird setup. They are. Well, there you go. So that gives you your light. Yeah, somebody with no Monday classes gets a 5-day weekend that week. Okay, so let's talk about probability. So probability is measuring how likely it is that something will happen. Now, there's a lot of technical jargon and vocabulary and probability that I'm not going to get into here. We're just going to cover the basics. Like I said, about a 15 or 20-minute crash course in probability. There are 3 types of probability. There's theoretical probability. There is empirical probability, and there is subjective. Now, subjective means with opinion in it, right? If you have an objective opinion or a objective statement or a subjective statement, A subjective statement has opinions in it. Objective is a statement of fact. So let's start out with that subjective. Subjective is basically an educated guess. Now, I don't want to get too far into gambling, but gambling is one of your better applications of probability. When they give you like the over-under for football games or the odds on a horse race, those are based on probabilities, but they are educated guesses. Nobody knows that the chances of this horse winning the race is only 10%. They're just guessing based on past performance and other races they've had with these same horses or races they've had under these conditions. You know, they would look at this horse runs better in the mud, so if it's raining out, they're going to lower its odds, so it's more likely to win. Things like that. It's subjective. They're just taking a guess based on past experience. It's not set in stone. They do adjust them, by the way, based on if they measure public opinion or general popular opinion. If a lot of people are betting on a particular horse, they lower its odds. They lower the payoff. So then people will be less likely to bet for it because it's not as big of a payoff. Well, stocks are not probability. That's a physical thing. Let's look at empirical probability. Empirical is relative frequency. Basically, if you look at this event, if option A happens 7 out of 100 times, well, then its probability is 7 out of 100, which is 0.07 or 7%, however you want to write it. That's its relative frequency. Theoretical probability is where the calculations come in. Theoretical probability is looking at number of successful outcomes. An outcome is just a result of an event over the number of total outcomes. I just put a lot of Greek up here and I realize that. So let's talk about this a little bit more detail. If I roll a die, a standard 6-sided die, the probability that that result is going to be a 2. How many 2s are on the die? 1. How many total possible results are there? 6. So it's 1 out of 6. If I wanted to make that into, I do 1.667. If I wanted to make it into a decimal, or 16.67%. So let's look at that theoretical probability a little bit more. Yep. Let's flip a coin. Now I'm going to make a little bit of a side statement to this. It's not just any coin, it is a fair coin. What does a fair coin mean? Well, it has it has two-sided. It doesn't, not both heads or both tails. There's one heads and one tails on it. But also that it's balanced, equally likely to come up either way. And a fair coin, what is the probability that you flip the coin and you get heads? Yeah, there's one head on the coin and there's two sides. So 1/2 or 0.5 or 50%. That is the theoretical. sometimes called classical probability. Our empirical, let's say we want to test to see if the coin is a fair coin. You flip the coin 500 times, and there's 236 heads. The empirical probability of getting heads on that coin is 236 out of 500, 0.472, right? Or 47.2%. Slightly less than half. Believe it or not, most coins are not totally fair. Because the shape, you've got the different pictures on the coins. Heads usually is slightly less or slightly more likely than tails, because if you're looking at a coin, if this is your coin, the profile of the head sticks out a little bit more than the profile of the tails. So the heads tends to rock more, so it's more likely to flip over if it hits on the head side. Where the tail side is flatter, it's more likely to stay there. So most coins are slightly more likely to hit tails than heads. There was an experiment done with this with the state quarters, and they actually did, the quarters from each state, and they flipped them a couple thousand times. Obviously, they had a little bit of spare time. They flipped them a couple thousand. They actually had a machine that flipped them, so it made sure it flipped them the same every time too. And it actually had the chart showing what was the probability of heads for each, and it was actually slightly different for each state coin, because the slight differences in the shape of the coin make it slightly change the balance of it. There are also ways of flipping a coin, by the way, that make it more likely to come up one side or the other, but we're not going to get into that. So those are our basic probabilities. Yeah, never gamble with the Math Geek. We're going to put marbles in a box. So what we're going to do is we're going to put in, I was going to mess with you, put 20 red and blue and 30 blue and red, but we'll do it. 20 blue and 30 red in a box. We mix them up really good. We hold the box so that we can't see what we're grabbing. We reach in and we grab a marble at random. We randomly grab a marble. And now this wording is actually very important. What is the probability that the marble we are going to grab is red? Well, how many red marbles are in there? 30. How many total marbles are in there? 50. So that's a 0.6 or 60%. What's the probability that the marble we're going to grab is, now, notice that the marble we are going to grab. If I said we reached in and grabbed a marble, what's the probability that marble is red? Well, probability doesn't apply there because the event has already happened. Probability only applies for things that are going to happen in the future. Once it has happened, it's a whole different story, and we're not going to get into that. But anyway, what's the probability that the marble we are going to pick will be blue? Yeah, 20 blues out of 50, so that's 0.4 or 40%. Well, that's the boring part. Let's look at the more exciting part of probability. I'm going to throw the word out there just because compound events. Compound events mean, of course, more than one thing happening. What's the probability that we reach in and we draw out two marbles and they're both red? Well, unfortunately, at this point, we do not have enough information to answer that question yet. Two technical terms or with replacement and without replacement. Because the probabilities change. With replacement means we draw out the first marble, we look at it and record its color, we put it back in the box, mix them back up, and then we draw out the second one. So if we do it with replacement, what's the probability that first marble is going to be red? 30 out of 50. What's the probability the second marble is going to be red? 30 out of 50. We put it back and it's still in there. So that is 900 out of 2,500, or 0.36. By the way, 0.6 times 0.6 is just 0.36. So you can just multiply the two probabilities together. Without replacement means we draw out that first marble, we look at it, and we toss it over our shoulder and draw the next one. Or we could draw both marbles at the same time. So there we did not put the first one back before we took the second one. What's the probability that the first one is red? 30 out of 50. What's the probability the second one is red? 29 out of 49. Well, I always get asked, how do we know that the first one was red? Well, we don't. But if it was blue, did we even bother drawing the second one? No. So we're assuming the first one was red, or we would have stopped. We'd have been done. So this is 30 times 29, of course, is 870. 50 times 49 is 2450. That divides out to be 0.3551. Slightly less than what it was with replacement. So I'm not going to talk a lot more about simple probabilities and marbles and stuff like that, because it's a little silly, but it gets that basic counting principle out there. We could talk about what is the probability that the second marble is blue. This symbol here means given that the first is red. Well, if we draw two marbles, if the first one's red, how many blue marbles are left in there? All 20 of them. How many total marbles are in there? 49. Now it's assuming there's no replacement, right? We took it out, took the red one out, tossed it over our shoulder. So that makes it slightly more likely. 20 divided by 49 is 0.4082. Where if we just were drawing out a blue one, it was just 0.40. Let's look at a company. And in this company, we have two types of employees: hourly wage and salary. No Bob and Steve this time. And we want to look at how they use their time off, their paid time off. So let's do sick or vacation. So let's say of those that are on a wage, 67 use their paid time off because they're sick. 33 use it for vacation. For those that are on salary, let's say 8 use their time because they're sick. 12 used it for vacation. This thing is what we call a contingency table. And what it is comparing two different variables or two different characteristics of a group of people and comparing them against each other. So what we have to do to make this work is we have to find the total for the rows Well, 67 plus 33 is 100. 8 plus 12 is 20. Then we have to find the total for the columns. 67 plus 8 is 75. 33 plus 12 is 45. Then, of course, the grand total better be the same in both directions of 120. What is the probability that a randomly selected employee will so I'm just randomly selecting an employee be on salary? Well, how many employees are on salary? 20 out of 120. 0.1667 or 16.67%. What's the probability that a randomly selected employee used their time because they were sick? 75 were sick out of 120, which ends up being what? 0.625, is that correct? So you can see we can find those probabilities relatively simple. So let's step it up a notch. Pretty good where we're at. What is the probability that a randomly selected employee is on wage? Come on. And uses their time for vacation. So now, here's the ones that are on wage. Here's the ones that use their time for vacation. What part of that are we really interested in? Only the ones that do both, just the 33. So that is 33 out of 120, which is, what is that, 275. So when it was an and, it had to be both of them. What is the probability that a randomly selected employee is on wage or uses their time for sick? So now here, or, here's wage, here's the ones that use their time for sickness. It can be either one of them. So what that means is I have to add up those three numbers. If I add them up, 67 plus 33 plus 8, of course that's going to be out of 120, right? I add them up, that's 108 out of 120, otherwise known as 0.9. There are other ways I could have come up with that last number. Yes. Yeah. Your sound is cutting in and out. So wage or sick, because this one here, even though it's salary, is sick. It's under the sick. Now, the other way we could have figured that out is we could have used the totals, the 75 and the 100. Well, you're thinking if I add 100 plus 75, that's 175. That's not 108. What's the problem with that total? The 67 was counted twice. So I have to subtract out the one that's counted twice. Guess what? That's still 108. Now here there's only 2 variables in each direction, so it's not so hard to just add up all the numbers. But if I had like 4 variables in each direction, rather than adding up 7 numbers, I could add up the 2 totals and just subtract out the one that was repeated in both directions. Okay. I'll brace myself for this one. What is the probability that someone uses their time for sick leave given they work on a wage? So let's ask what this here means here. Given that they work on the wage. What that means is we know something about the person we've selected. We know that that person works for wage, not salary. So what that means is, are we looking at all 120 of them anymore? No, we are only looking at the 100 people that work on a wage. So there are 67 that use their time for sick. Out of the 100, that's 0.67. So now I'm going to ask you, will this be the same problem? What's the probability that randomly selected employee works on a wage given they use their time for sick leave? Is that the same question? No, it's not. Now, given sick leave, that means we know they use their time for sick leave. So we're only looking at the people that use their time for sick leave. How many of them work on a wage? 67 out of 75. Gives us 0.8933. What's the probability that randomly selected person works on a salary given that we know they use their time for vacation? I'll give you guys a couple minutes to, not a couple minutes, about a few seconds to figure this one out. We'll discuss it. So probability that they work on a salary given they use their time for vacation. So the first question is, does that mean we're narrowing it down to the salary or are we narrowing it down to the vacation? We're narrowing it down to the vacation. We know they use their time for vacation. So then the salary would be 12 out of 45. Yeah, 0.2667. What do you think? Those contingency tables, I said this is a very simplified example. Those contingency tables appear a lot in business, comparing different things. I might show, level of education compared to what type of job position they have in the company, whether it's production, sales, management, whatever. All sorts of things you can compare and get a very, very good, valid analysis off of. Okay, that is it for new material. So what I want to do is I want to take the rest of the time for answering questions on the test. If you have done all your test corrections or you don't have any questions on your test corrections, I'm going to give you guys a couple of minutes if you want to pack up and leave, or if you want to hang around, that's fine too. But just so that we don't have a lot of commotion going on as we answer questions, I'm going to pause for a couple minutes here. My answers, do you guys want me to leave the recording going so your answers to your questions on the test are on here? Sure? Okay. So I'm just going to pause the recording for, I'm just going to turn the recording on here. Number 21 is just asking, convert to a fraction 18.5%. Yep. Oh, sure. You bet. 39. I knew that one was coming. 37 over 200. That's 18.5 over 100. If you double it, that's 37 over 200. Got to do both of them times 2. Oh, 185 over 1,000 and reduced it. Should still reduce down to 37 over 200. Oh, sure. Yeah. Yeah, number 39. 39 is a simple interest formula. I give you I equals PRT. In the problem, we are told, find the rate. So we're looking for R here. We're a principal of 24,000. Interest of $160. And the trick here is the time. Well, it's 1 month, so the time is 1/12. So to solve this, we need to combine the numbers on the same side. So the 24,000 and the 1/12 makes 2,000. To get R by itself, you divide by 2,000. Yep. That's all multiplied together, so you're just multiplying. So what you'd be doing is you'd be taking 24,000 times 1/12. So times 1 divided by 12 gives you the 2,000. Nope. 160 equals 2,000 times R. Then you have to divide by 2,000 to get R by itself. So 160 divided by 2,000 is 0.08 equals R. So you'd either leave the rate as 0.08 or 8%. Either one would be acceptable. Okay. Any other problem numbers you want me to go over? Ashlyn, do you have any you want me to go over? Okay. You didn't get it back? Anthony, right? Yep. It should be in the grade book now. I graded it earlier today, so it should be in the grade book now for you. Nope, you had them all right. Okay. What's that? Yeah, it says to the nearest hundredth of a percent. 18 point. It's because 18.599. So it should be 18.60. Number 32. A lot of people struggle with number 32 because it's a percent change problem, and the number I gave you is after the change, not before the change. So number 32, the price of Delta Airlines tickets from New York to Orlando increased to $450. So we have an old price. We're adding to that old price an increase to give us a new price. You bet. So on the percent side of this issue, we have the old price, come here, was 100%. This was an 8% increase, so the new price is 108%. On the dollar side, we know that the new price is $450. And we want to know what the old price was. So that means we don't need this middle row at all. We need the row that has both numbers, which is the new price, and the row that has the number we're looking for, which is the old price. And I don't know why my highlighter didn't work there, but it's okay. So those are the rows we need. So what two numbers are diagonal to each other here? So we're going to multiply those. So it's 45,000. So then the other number is the 108. We're going to divide by that. This is 416.67. Yep. A lot of people put 414 because they found 8% of 450, which is 36 bucks, and subtracted it. The problem is the 8% doesn't come off the 450. The 8% comes off of whatever the old price was, the 416.67. Okay, sounds good. Any others? 36 first. So number 36, erasers cost $5 per carton. Pencils are $7 per carton. So a total of 15 cartons for $85. So let's let the number of erasers sold or the number of pencils sold be X. The number of erasers sold, since there's a total of 15, would be 15 minus X. The dollar amount from each then would be their price times the number sold. So for erasers, it's 5 times the 15 minus X. For pencils, it's just 7 times X. So the money from the erasers is $5 times, there's 15 minus X is the number that was sold. Yeah, we'll get to that. Plus, the amount for pencils is 7 times X, which is 7X. That has to add up to 85. So yes, now what you're going to do is exactly right. We have to distribute the 5. 5 times 15 is 75. 5 times negative X is negative 5X. And we have the positive 7X equals 85. Oops, my power just went out here. Let's get that back up. So now to combine there, this is my screen. Thank you. Waiting for the screen. There it is. There we go. It'll be just a second. It'll be back up there. So now we're going to combine negative 5X and 7X is a positive 2X. So that's 75 plus 2X equals 85. And then we solve that equation. So you subtract 75. So 2X equals 10. Have a good week. You divide by 2. Gives you X equals 5. So now we got to go back and figure out what X was. X was the number of cartons of pencils. There's 5 cartons of pencils. Then we got to do 15 minus X. 15 minus 5 is 10 cartons of erasers. Yep. He said number 40? Number 40 is another one of those wordy problems. Jim Smith has 2 options in buying a computer. The first option is cash, $425. Option 2 is payments. And that is $60 down plus 15 payments of $28 each. So here we do the 15 times 28, which is $420. So that's the total amount of payments plus the $60 down payment. $480 total. So then it's asking is what is the difference? How much more does it cost to make payments? So the difference between 480 and 425. Yep. $55. You got it. Any others? That's all of them? Okay. Perfect.